Great to see you here again. My name is Luc de Ceuster. I'm founder of the Ceuster Academy, and in this video I will talk to you about another exercise related to the Chinese Remainder Theorem. This exercise will be a little bit different. There are some particular things that we have to do, but we will see that in a few seconds. But first, before we start, do not forget to click the subscribe button, click the bell button, so every time we have a new video, you will be informed about it. In the previous videos, we looked at the classical approach to the Chinese Remainder Theorem, and we had linear congruences of the form x is congruent bi modulus mi. And the x coefficient, or the coefficient of x, was equal to 1. In this exercise, we have it a little bit different. We have 3x is congruent 5 modulus 7, and 4x is congruent with 6 modulus 26. The first thing that we have to do is, in fact, transform these equations in the classical form. So we have to transform this as x is congruent with a constant modulus 7. Now, when we look at this, what we see here is that the GCD of 3 and 7 is equal to 1, which means that the 3 modulus 7 is inversible. And what we can do now is to find the modular inverse of 3 modulus 7. So we have 3 modulus 7, and we have to find basically the modular inverse. Now, when we look at this, we can already see what we have here. And when you get a little bit more experience in these calculations, you can immediately see when I multiply 3 with 5. 3 times 5 is 15. And 15 modulus 7 is equal to 1. So when we say the modular inverse of 3 modulus 7 is equal to 5, so we multiply both sides with 5, we find 15x is congruent with 25 modulus 7. What we know, 15 modulus 7 is equal to 1. So we find x is congruent 25 modulus 7, but 25 we can also write as 25 is 3 times 7 plus 4. So basically the modulus, 25 modulus 7 is equal to 4, so we find 4 modulus 7. And that's basically the first equation that we will use in our system. So that's the first thing that we did. The next thing here, the GCD of 4 and 26 is not equal to 1. Now, what we have to look at this, we have to see, we can say that we have a common coefficient. So we can say this is 2 times 2. X is congruent 2 times 3 modulus 2 times 13. And what we can do now is divide both members by 2. So I find that 2x is congruent with 3 modulus 13. And now the same thing. We have to get this x still out of this expression. Now, we see, or we can calculate it, we see when we multiply 2 with 7, we find 14. And 14 modulus 13 is 1. So when we multiply both sides by 7, I find here 14x is congruent with 21 modulus 13. And this is equal to 1, or x, we just write x, is congruent 21 modulus 13. Well, 21 is 1 times 13 plus 8, so the remainder is 8. So we have 8 modulus 13. So basically what we did now, this is the second expression, and we have in fact transformed those two equations into a new system of equations that we will resolve using the Chinese Remainder Theorem. And the new system is x is congruent with 4 modulus 7 and x is congruent with 8 modulus 13. And we know that the GCD of 7 and 13 is equal to 1. So, this is logical, 7 and 13 are both prime numbers. Of course, they are relatively prime, their GCD is equal to 1. And this means that we can find a unique solution for this and this system of linear congruences. And let's do that, but first I have to clear the board so I have more space to do all the calculations. We found the new set of linear congruences, and based on this we can continue with the next steps. We already verified that the GCD of 7 and 13 is equal to 1. They're relatively prime, they're both prime, so that's obvious. And we know that according to the Chinese Remainder Theorem, we have one unique solution for this set of linear congruences. The next thing to do is to calculate m, the modular value. So we have 7 times 13, which is 91. So our solution will be congruent modulus 91. We have m1, which is m divided by 7, which is 13, and m2 is equal to 7. So that's very easy to find because we only have two numbers here. Now, based on this, we can write the new expressions. We can say that we have m1 x1 is congruent with 1 modulus 7, and when we replace the values here, we have 13 times x1 congruent with 1 modulus 7, 13x1 congruent to 1 modulus 7. We can simplify this, everything modulus 7, so we have 6x1 is congruent with 1 modulus 7, and now we have to find the value that gives us that, let's say, the inverse, the modular inverse of 6 modulus 7. So when we do this times 6, 36, when we look at modulus 7, 36, and we have 7, so we have 5 times 7. So basically we can say 36 modulus 7 is equal to 1. So we find x1 is congruent with 6 modulus 7. And that's the first value for x1 is equal to 6. Now we do the same thing for m2 x2. m2 is 7, so we find 7x1 x2, sorry, it has to be x2, is congruent with 1 modulus 13 now. And we find here, well, we can see immediately when we multiply both sides by 2, we find 14, and 14 modulus 13 is 1. So we multiply by 2, and we find x2 is congruent with 2 modulus 13, which gives us that x2 is equal to 2. And basically those are the two values that we need. We need x1, we have x2, we have m, we have m1 and m2. And now we can say that x is equal to the sum of I equal to 1 to 2, bi times xi times mi, and we will find the final result here. But before we continue with this, I will make a summary of what we found, and then we calculate the final result. In the table, I summarized the results that we had before. b1 is 4, and b2 is 8, x1 is 6, x2 is 2, m1 is 13, m2 is 7. So when we multiply 4 times 6 times 13, we find this is equal to 312. And then we have 8 times 2 times 7 is 112, which gives us a total of 424. Now this is a solution modulus m, and m is 91. So what we can say, we have 424 modulus 91, which is equal to 60. We can say that 424 has a remainder of 60 modulus 91. Now what we have to see here is that we have here 91, which is the product of the moduli of the two reduced equations. But what do we have? Basically, originally, m original was the double, 182. So basically, we have to adjust this solution to the new modulus. And we have then 60 modulus 182. And the second one, we add 91 to this, because there is a difference of 91, is 151 modulus 182. And basically we have two solutions here, 60 and 151. So that's the way how we deal with a system of linear congruences where the x has a factor. And we also see that the GCD here is not equal to 1, so there is more than one unique solution. Of course, we have to transform or convert those equations in the form x is congruent with b modulus m. Once we have done that, we can find a solution, but we have to adjust that solution, and we have to add more solutions which are congruent to the original product of the moduli. So in this case, the reduced modulus was 91 and the original was 182. So we have to have an additional solution here. We have to add the 91 to the original solution and review everything modulus 182. That was it for this exercise. Do not forget to read the text below the video. You will find very interesting links to different courses and coupons that will give you a great discount when you decide to buy the course. It's the end of the video. You can still subscribe by clicking the button here. You can subscribe to our channel. Click the bell button so every time we have a new video, YouTube will let you know. Thank you and bye-bye.